Hello once again, it's Mr. Pete, your YouTube shop teacher, and you are watching Tips 804. This is part 2 of a 4-part video where I retrofit this 9-inch Model C South Bend lathe into a Model B, and that consists of changing the apron from the old to the new, and this was given to me by Roger Taylor. And I ran into a little bit of a snag. I thought it would be a real easy job, but there are no easy jobs, I guess. But the problem that I ran into, and what I'm going to do in part 2, is make a gear that will fit onto the old screw. Now, this is the screw that I took out of here. This is the one that Roger gave me. It has a gear on it, but it's quite a bit different. It's longer and the dimensions are different. So I cannot use this. I have to use this, and I'm going to make a very small gear that'll go on right here, and I'll do that on the Clausing horizontal milling machine with some degree of difficulty. You've all seen me cut gears before. I'm going to try to simplify this. I'm not going to do much of the math because people do not like that and probably will never cut a gear, but you might still find this of great interest. And then in part 3, I'm going to cut a keyway onto the lead screw, which you cannot see right here. And then in part 4, hopefully, if I get that far, reassembly of the whole unit and testing to see how it works. So let's begin, shall we? All right, let's get started here. Enough talking, but if you don't want to hear any of this related information, just advance until we get into the gear cutting itself. But some of this related information is necessary if you actually were to do this. I will try to minimize it, and I'm not going to talk much about the mathematics of it at all. You don't really need to know that, actually, unless you're an engineer. But again, this is the original that I am replacing by putting a gear on it. This is the one sent to me by Roger, and you're probably saying, well, why don't you just go ahead and make an entirely new shaft, because this gear is integral. So imagine starting with a piece of 3/4, turning it down. This is a left-hand Acme, which isn't particularly easy, and we've got undercuts here and steps and shoulders, and we've got a keyway here and a hole. So there's just all kinds of things that would have to be done in order to make this. So I don't intend to do that. I'm lazy. I want to do it the simplest way, and that will be to produce this gear. And I've already done a sample, and this is more or less what it looked like when I cut it, with a hole on a piece of 3/4 shaft turned down. And then my game plan is to put this gear onto this part right here, and I'm going to use some industrial grade permanent Loctite to hold it on. Of course, it could be pinned, but that would weaken the shaft, I believe. You could have a set screw, but I don't know where you'd put it. There's just a lot of interferences. You could braze it. No, I don't like that. You could silver solder it. I think my method with a really strong Loctite is excellent. And if you need to get it off, you just need to heat it, not even with a lot of heat. Just warm it up really, really good, and you can twist it off there. Because, in fact, I've already had it on there, and I took it back off for the purposes of this video. If you desire to know much more about gear cutting, start with this video of mine, and there are 3 or 4 or 5 of them in all that you can watch and study. If you want to read up on this subject, there are countless books, and this is a great book from the 40s or 30s, Gear Cutting Practice. Much more than you need to know, because we are only interested in spur gears. Also probably a lot of information available on the internet. This is a real old book that I have in my library. It's about 1 inch thick, and it just has so much information about gears and gear cutting. More than you need to know. Also, there's a lot of information in the old Boston gear catalogs. The first thing we have to do is to identify this gear and come up with a gear cutter. So I measured the diameter, and it is 700 thousandths, a little less than 3/4, and I counted the number of teeth. There are 12 teeth. It's a very small gear. Matter of fact, it's the smallest gear I believe that you can cut in this diametral pitch. Now here is how I determined the diametral pitch. It's a simple method. Anyone can do it in a matter of 1 minute. Count the teeth. I've already done that. There are 12. Add 2 to the number of teeth. That would be 14. And divide by the gear diameter. And I just measured, and the gear diameter is 700 thousandths. So 12 plus 2 is 14. Divided by 0.7. And the diametral pitch is 20. Very easy to do. There are other ways as well. I do not own one of these gauges, but the Boston Gear Company makes a set of gauges that look very similar to thread pitch gauges. They also make a set of gauges that would be used on racks, and of course a rack is nothing more than a linear gear. Okay, looking in this book, you can also see that they have diagrams here of various gear tooth configurations, and you could match it up. For instance, ours again is a 20 diametral pitch. Not too easy to do with this, because how are you going to match that up? I guess you could. I know my fingers are in the way, but that's one other way of doing it. As long as I got this book open, on the facing page are all of the formulas that you may or may not need when calculating for gears. And all of that information is probably available in many other books as well as the internet. One other resource for all of your machine shop mathematical needs is the Engineer's Black Book. And there's a nice page here, actually 2 pages, on gear cutting, again talking about all of the math and the formulas and some diagrams here, and there you can see that how you would calculate the depth. But remember, you don't need to do some of this because it's done for you. If, for instance, the depth is marked on every cutter. Now here's the hard part. You have to have the correct gear cutter in order to do this, and I have a full set of these. Actually, there's 8 in a set. The one that I'm going to use is already mounted on the milling machine. That's why you only see 7 here. Every one is marked with a number and the number of teeth that it can cut. The bore on this is only 3/4, so I had to use a homemade arbor to hold that. None of my commercial ones are that small, but it'll work fine, and you'll see that when we get into the cutting. Let me say a few more words about this. I guess I failed to say that the cutters I just showed you are 20 diametral pitch. You would have to have another set of those if you were cutting gears of a different pitch. Okay, what is pitch? I'm not even going to explain that. It's the different sizes. You can look that up if you want. But in the old Brown & Sharp catalog here, you can see that there are 8 cutters in a set. I am using cutter number 8, which allows me to cut either 12 or 13 teeth, and I am going to cut 12. If you're going to cut a rack, you'd use the number 1, and so on, right on down the line. I think that you are probably able to buy just a single cutter rather than a whole set, because more than likely in your lifetime you're never going to use some of them. I bought these gear cutters several years ago, and of course they came from communist China. I wrote the depth down because the depth of the tooth is 0.108. They are 20 diametral pitch. That's when I bought them, I guess. And they have a 5/8 bore. And of course the gear has to have a hole in it that will allow it to fit with a real good fit onto this diameter here. And of course that's a weird diameter. It is in fact 443. 437 would be 7/16, so I will drill it 7/16, which will not be the right size, and then I'm going to have to ream it. Well, that's an odd reamer, so I'm using one of my adjustable reamers that I already spent a half hour setting, so it's just the right diameter to take just a few thousandths off of the hole that I drilled, because no doubt the 7/16 will drill just a little bit oversized. They typically do. We always want to start with a piece of material a little bit longer than what we need because it has to be held in a collet and a chuck and all of that. So this is 3/4 mild steel. Again, I've already cut a sample, actually several samples. I always rehearse, you know. Do you rehearse? If you're a maker out there, do you rehearse? I do. Anyway, I will face this off on the lathe right behind me, and then I have to turn it down to that diameter that we just talked about. And I already forgot. What was that diameter? 700 thousandths. So let's step over to the drill. Not the drill, the lathe, and I will face that, drill it and turn it, and then I'm actually finally ready to cut the gear. There's a lot of steps involved in this, isn't there? That's why this video is so long. I am so happy to finally have a 5C collet attachment on my closing lathe because they run so true compared to a 3-jaw chuck. So that's what I'm using. The work is already mounted. A stop is set for the length, and I'm using high-speed steel here, and I'm going to turn her down again to 700 thousandths. That's not a whole lot off of 750. Okay, the blank is about ready for gear cutting. I have center drilled, and I drilled a 1/4 inch hole as a pilot. I'm not going to drill it 7/16 until after the teeth are cut because it might lack a little bit of rigidity. I do not want it to vibrate or flex as I cut the teeth. So that can be held over easily. I've cut a lot of gears over the years, and I've used the Bridgeport most of the time, but I think it's better done on a horizontal mill, and I normally used this little index head or dividing head. It's a Hardinge brand, but I'm not going to use that today. I'm going to use a spin index, which will actually make it much easier. We don't have to worry about any of the calculations for the index plate. It's just like super easy. So I'll get to that in a minute, but this is what the blank looks like to this point. So I will cut it just like that. We'll step out to Studio G, which stands for garage, and we will begin, and I'll talk a little bit about that spin index. For your information, I'm going to use a spin index that looks just like this, and I've had mine forever, and they're still only $77 without the collets. They use a 5C collet, which you probably already have, and they're just really simple to use. And here is the math. Since we have 12 teeth, and we're going to go in degrees here. If you divide 360 degrees of a circle by 12, you'll come out with 30 degrees. So we're going to cut a tooth, and then we're going to rotate this 30 degrees and cut the next, and so on until we have 12 teeth cut. Here we are in Studio G, and I'm going to be using this beautiful little closing horizontal mill donated to me by Chuck Kavaznicka up in Detroit area. Thanks, Chuck. It's a little difficult to see here because everything is so tight and it's hard to get the right light, but I already have a 3/4 collet mounted in the spin index, and I'll simply hold the work like that with just enough sticking out so that I do not strike the collet or the fixture with the cutter. And the cutter is already mounted, the number 8 cutter. So let me tighten up the spin index real well so the work won't slip. There are no keys located on the bottom of the spin index, so it's just free to wander around. So I've squared it up, and I've even checked it with an indicator off camera so that the work is perfectly parallel with the slots on the table, and I've got a clamp here and a clamp on the other side, so it's not going to move. There's not a whole lot of force against it. I've already set the machine for a speed of 500 RPM on the spindle, and I'll have to run it in reverse, the motor in reverse, because of the direction of the cutter. I'll be cutting toward the spin index. So again, that's reverse, and the speed 500 RPM, and feed is about 1 inch per minute, 1.06. I'll be using the power feed. And I've already set a stop so it will trip off, that's right here, when I get to the right length of tooth. It's so tight in here I have to hand hold the camera, so it's kind of shaky, but I have already set the cutter so it's exactly on the center line of the work. If it's off one way or the other, the teeth will be cockeyed and it's going to bind and it won't work. So it will take too much time to show all that, and I've shown in other videos. So that's been done already, and the next thing I have to do is set the depth, and I will do that by putting a piece of tape on the work and then turning the machine on, and I will raise the table until I scratch the tape. I think I can show that if I can get the camera in. And then I will raise the table up the full depth, which is 106 thousandths. All right, I'll turn the machine on and up it goes until I scratch the masking tape. Can you see that? Now I've backed the work off so I won't touch it, and I will raise the knee here with the crank. Again, 106 thousandths. It's set on 0. And with this milling machine, one full revolution is only 50 thousandths, not 100 like we are used to on a Bridgeport. So there's 50, 106. From this view, again, indexing could not be more simple. This is a lock. And when I pull the pin out here, and I will not use any holes here other than the 0 pin, which I'm in right now, and I can read right here, I don't know if you can quite see that, it's on 0 degrees. Can I zoom in? Yes, I can. There's a pointer right here, so I'm on 0 degrees. I will cut one tooth. Then I will stop, turn off the machine, always turn it off, loosen the lock, pull the pin. You don't have to pull it all the way out, I just am not in frame, and then I will just turn this, or the crank, whatever, until we get to 30 degrees, right there. Push the pin in, like that, lock it, cut another tooth, and then back it off, loosen this up, pull the pin, move it another 30 degrees, which in this case is 60, lock it, and so on. Now I'm going to put that back on 0 because that is my starting point. You can see how really simple this is. Now you're not going to be able to see this as we cut the gear, and in fact I'll only be cutting 2 or 3 teeth for the purposes of this video. It's already pretty long, isn't it? Pay no attention to the dial indicator. I cut one of the gears using that as my stop, and I set a block here, and I would just cut until I got a 0 reading here on this indicator. I left it in place, but in fact, as I told you, I've already set a stop for the power feed, so that's how I'm going to actually cut. So I am at this point finally actually ready to cut. Now I am using a little bit of oil, and as always, no matter what machine you're using in your shop, be sure and wear your safety glasses. This is a machine that is very easy to get wrapped up in, so wear short sleeves, have no rags or anything else that might get caught. Now you're going to see that the cutter does not run true. That is, it's loping. And in all of my years' experience, I've never ran a milling machine where there wasn't some run out like that. And I notice when I watch other people's videos, they have the same problem too. I thought maybe it was a bent arbor or other problems, but I even remember that when I was a high school student that happened, and I always wondered why. But we're not going to worry about it because it'll come out okay. And here we go. And we are now 1/12 of the way through. I have cut 11 teeth. I have one more to go, and it looks like it's going to come out even. Don't stick your finger in there with the machine running. If you end up with one thick tooth and one thin tooth, you might as well walk right over to the scrap bin and throw it away. All done. The reason I left the indicator in place is I was unsure how accurate that cutoff was on the power feed, but it always came within about 2 thousandths, so it was quite accurate when it cut off. All right, it's done. Take it out. And do not take it out until you are done. You'll never get it back in the same. Looks pretty good, doesn't it? I don't see any thin ones. Let's go back down into the basement shop and cut it off. Okay, this is the one that I just cut 2 minutes ago, as you can see. And let me explain something now. Rather than make the gear like this without the tapered part, whatever you call that, where I complete the cut. Ideally, I think we'd like it to look like that. Although even on this one, you see what I'm talking about there. But the reason I want to leave that on is because this has become very thin-walled and almost what I would consider delicate. But I think that this gives it a little extra beef on the end. Matter of fact, I know that it does. Also, when I made this one, I found out that I needed this undercut here because this was striking the casting. I might show you that if I remember when I actually install the screw into the machine in part 4. So without showing you everything here, I'm going to go over and cut this off on the bandsaw right about where the tip of my finger is, and then back onto the lathe, drill that 7/16, which I might show, along with reaming it. So I'll see you in a minute. It's about a half hour later, and I turned this down to that clearance as I showed you on the other one, and I drilled it 3/16 all the way through. However, it's still a little bit too small, as we discussed earlier. It will not go on to this diameter right here, so I will use this adjustable reamer that's already been set just in the vise, holding it very carefully. There's only a few thousandths to take off, and I will ream it. And it now fits perfectly. And one more thing to do before I put the Loctite on, and that is to face it to length. It's still just a little bit too long. I only want it as long as the step. Actually quite a bit that I have to take off. I'll do that off camera. Okay, I shortened it up a bit, and I just cleaned the bore and this step right here with some thinner, and I'm ready to use this Loctite. I'm not sure of the number, I can't read it, but it's the permanent stuff. I've had really good luck with it, even though it's ancient. And on it goes, and it has to set overnight. And when I'm done, I'll put this in the chuck, and I'm going to run a file over here just real gently to clean it up, and then it's ready to install. And you'll see that in part 4 when I finish the job. In part 3, which is the next part, I will put a keyway into the lead screw, which is also a necessary part of this job. And remember, you can do all of this on your lathe too. It's a simple job. It's just that you need $50,000 worth of equipment. Well, I hope you enjoyed this video and my other ones. That concludes this part 2. Be sure and watch part 1 and part 3 and 4 when available. This is Mr. Pete saying so long for now.